On Monday, you will see headlines that say, "A newly discovered asteroid will safely pass Earth." And every word of that will be true. It will pass. It will be safe. What the headline will not tell you is that we found this thing only 8 days before it arrives, that an object this size is almost always found that late, and that if it were coming straight for us, we would have no way to do anything but watch. That is the part nobody puts in the story. Over the next hour, I am going to give you the whole story, the one underneath the reassuring version. Stay with me, because by the end, the word safe is going to sound very different. If this is the kind of thing you want to understand, not just hear about, subscribe to The Quiet Archivist. Drop a comment with where you are watching from, and whether you will be tuning in to the Flyby livestream Monday. Now, let's get into it. Somewhere above your head right now, moving at a speed you cannot feel and cannot see, there is a rock that has an appointment with Earth. The appointment is on Monday. And the unsettling part is not the rock. The unsettling part is that this rock has a name that is only about 8 days old. Let me tell you what we know. And then let me tell you why what we know should bother you more than the headlines are letting on. The object is called 2026 JH2. That designation is the only name it has, because until a week and a half ago, nobody on Earth knew it existed. On Monday, May 18th, 2026, at roughly 21:23 Universal Time, 2026 JH2 will pass Earth at a distance of about 56,500 miles. That is about 91,000 kilometers. In the language astronomers use for this kind of thing, it is about 0.237 lunar distances. Now, that phrase, lunar distances, is doing a lot of quiet work, so let me unpack it. The Moon orbits Earth at an average distance of about 238,000 miles. That is the gap you are looking at when you look up at a full moon. 2026 JH2 is going to cross that gap and keep going, and it is going to pass us at a little less than a quarter of the way out to the moon. Think about that. Not past the moon, not at the moon. Inside the moon's orbit, by a wide margin, and it gets closer to home than that. There is a ring of satellites circling Earth at an altitude of about 22,000 miles. That is where a lot of our communications hardware lives, the geostationary satellites that sit fixed over one spot on the planet. 2026 JH2 is going to pass us at more than twice that distance, so it is not threading through our satellite belt, but sit with the scale of it anyway. This asteroid will, for a few hours on Monday, be closer to the ground than a meaningful fraction of the machines humanity has bolted into the sky. It is a visitor that comes inside the room, not one that waves from the doorway. So how big is this thing? The honest answer is that we are not completely sure, and the reason we are not sure is itself part of the story. The best current estimate from the people who track these objects puts 2026 JH to somewhere between about 16 and 35 meters across. In feet, that is roughly 50 to 115 feet. Picture a decent-sized house at the small end, and something closer to a small office building at the large end. That estimate, by the way, is not a measurement. Nobody has put a radar beam on this rock or read its heat signature. The size is derived from how bright the object looks, and an assumption about how reflective its surface is. That is the standard way you size a newly found asteroid before the better instruments can get a look, and it means the real number could sit anywhere in that window. Here's why that size range matters. An object between 16 and 35 meters across is not a planet killer. It is not the thing from the movies. It would not end civilization, and on most impact scenarios, it would not even be a regional catastrophe. But it is not nothing either. An object at the upper end of that range is in the same size class as the body that exploded over Chelyabinsk, Russia, in 2013. That one came in, detonated in the atmosphere, and the shockwave blew out windows across 6 cities. Roughly 1,500 people were injured, almost every one of them from flying glass. One astronomer, talking about a flyby like this one, put it about as plainly as you can put it. He said an object like this is the kind of thing that would, and I am quoting, ruin a city quite efficiently if it hit. If it hit. Hold on to those 3 words, because they are the hinge this whole story turns on. 2026 JH2 has been classified as an Apollo-class near-Earth object. That classification sounds technical, but the idea behind it is simple and a little ominous. Apollo asteroids are bodies whose orbits cross Earth's orbital path around the Sun. They spend most of their time farther out than we are, but their elliptical paths swing them across our lane, the way a car can spend most of a trip in its own lane, and still, at certain moments, drift across yours. Apollo objects are the most populous class of the potentially hazardous orbit types. They are the class that produces most of the close approaches we record. And they are the class that produces most of the actual impacts. But none of that, the distance, the size, the orbit class, is the thing that turns 2026 JH2 from a routine flyby into a story worth an hour of your time. The thing that does that is the calendar. 2026 JH2 was not on anyone's list 2 weeks ago. It was found on May 10th, 2026 by the Mount Lemmon Survey, a telescope program operating in the Santa Catalina Mountains, north of Tucson, Arizona. It was announced to the world through the Minor Planet Center on May 12th. Follow-up observations came in from other facilities, including the Farpoint Observatory in Kansas, and its closest approach to Earth is May 18th. Do that arithmetic. From the moment we first knew this object existed to the moment it makes its closest pass is about 8 days. I want to be completely clear about something, because I do not do fear without facts on this channel. There is no impact threat from 2026 JH2. None. Every orbital model we have shows it passing us and continuing on its way. The calculated chance of an impact is a fraction of 1,000%. On Monday, it will go by. The astronomers will get their data, and that will be that. So if it is safe, why are we here? Why give an hour to a rock that misses? Because the part of this that should keep you up is not whether 2026 JH2 hits us. It is this. A house-sized asteroid was able to come within a quarter of the moon's distance of this planet, and we found out about it roughly a week beforehand. Not years beforehand. A week. And here is the sentence I need you to really absorb. If this particular rock had been on an impact trajectory instead of a near-miss trajectory, the warning time would have been exactly the same. 8 days. The same 8 days. Whether it was going to miss us or hit us. The flyby on Monday is safe. What the flyby exposes is not. And that is what the rest of this is about. When most people hear that astronomers found this asteroid only 8 days before its closest approach, they have one immediate reaction, and it is the wrong one. The reaction is, they found it late. Somebody messed up. The system failed. And I understand why that is the instinct. 8 days does not feel like enough. It feels like a smoke alarm that goes off after the house is already warm. But I want to walk you through why that instinct is wrong, because the truth is stranger and, frankly, more disturbing than a simple failure. Nobody messed up. The Mount Lemmon Survey caught this object. It did its job. The Minor Planet Center processed the observations and got the word out within 2 days. Other observatories confirmed it. From a process standpoint, the machine ran exactly the way it is built to run. The system worked. That is the problem. The system worked, and the system working still means 8 days. Here's the thing. almost nobody outside the field understands. For an object the size of 2026 JH2, a few tens of meters across, 8 days of warning is not a fluke. It is not a near miss in the detection sense. It is roughly the expected, normal, design performance of the entire global network of telescopes that hunt these things. When a rock this small is found about a week before it passes, that is not the alarm going off late. That is the alarm going off exactly when the alarm is built to go off. Let me explain why an object like this is so hard to see until it is almost on top of us. 2026 JH2 has an absolute magnitude of around 26.1. You do not need to know what that number means in detail. You just need to know which direction it points. It points toward faint. Very faint. This is a small, dark, fast-moving piece of rock, and for most of its orbit, it is simply too dim for our survey telescopes to pick out against the noise of the sky. It only became findable when it got close enough, and therefore bright enough, to cross the threshold of detection. And by the time a small object crosses that threshold, it is, almost by definition, close. Close in space means close in time. The brightness and the deadline arrive together. You can actually see the fingerprints of that on the data we have. In the first days after 2026 JH2 was announced, the Minor Planet Center had logged only about 24 observations of it. 24. That is a thin file. And because the file is thin, the orbit is not nailed down with perfect precision yet. This is why, when I told you the closest approach is at 21:23 Universal Time on Monday, the honest version of that sentence carries an error bar of about 6 hours in either direction. 6 hours of uncertainty on an event that is days away. Earlier solutions actually put the close approach a little later, near 21:57. The number is converging as more observations come in, but the fact that it is still converging this close to the event tells you how little arc, how little observed path we have to work with. We are refining the trajectory of this thing in real time as it comes. Now zoom out, because the 8-day warning on this one object is a window onto something much bigger. It is a window onto the state of our catalog of near-Earth objects as a whole. And the catalog is wildly uneven, depending on how big the object is. For the truly enormous objects, the ones a kilometer across and up, the civilization enders, we are in decent shape. The catalog for that size class is believed to be more than 90% complete. We have found the overwhelming majority of the genuine monsters, and we know where they are going to be for a long time. That is real, and it is reassuring, and it is the success story planetary defense rightly points to. Step down to the next class, though, and the picture darkens. For objects 140 meters and larger, the size capable of regional devastation, wiping out a metropolitan area and its surroundings, the catalog is far less complete. The working figures from the planetary defense community put the fraction we have actually found at somewhere around 40%. And there is a stated goal set years ago of cataloging 2/3 of that population. We have not met it. We are not close to meeting it. And then you get to the size class that 2026 JH2 actually belongs to. Tens of meters, the Tunguska and below range. And here the catalog is not just incomplete. It is radically, almost completely incomplete. The fraction of objects this size that we have found and tracked is down in the low single-digit percentages, or less. The overwhelming majority of rocks this size are simply unknown to us. They are out there, on their orbits, crossing our lane, and they will stay unknown until each one individually gets close enough and bright enough to trip a survey telescope, which, as we just established, usually means days of warning at best. So let me reframe the whole thing for you, because the reframe is the point. The anomaly here is not that we found 2026 JH too late. The anomaly is that finding it late is the system operating exactly as designed, and almost nobody knows that. The public hears newly discovered asteroid will safely pass Earth and files it under good news, mild curiosity, move on. What the public is not told is that the 8-day warning is not the exception. For this size of object, it is the rule. And I have been talking this whole time about one half of planetary defense. The half that finds things. Detection. And here's the genuinely uncomfortable part. Detection, incomplete as it is the half that works. It is the half that is improving. It is the half doing its job on Monday when 2026 JH2 slides past us right on schedule. So, what about the other half? What about the part where you find the rock, and then you do something about it? Where is that? That is where the hole is, and we need to talk about the hole. Planetary defense, as a concept, has two halves, and they are not equal. The first half is detection. Find the object. Figure out where it is, how big it is, where it is going. We have spent decades and real money building this half. And while it has serious gaps, especially for small objects, it functions. Telescopes scan the sky every night. Software flags the moving dots. The Minor Planet Center collates it all. That half of the machine is running. The second half is response. You have found the rock. It is coming. Now what do you actually do? This half is where the story gets thin, because this half barely exists. Let me give the response side its due first, because there is one genuine, real accomplishment here, and it deserves respect. In 2022, NASA flew a mission called DART. The letters stand for Double Asteroid Redirection Test, and the test was exactly what the name says. They took a spacecraft and they flew it, deliberately, at high speed, straight into a small asteroid moonlet called Dimorphos, a kinetic impactor, a cannonball essentially, aimed with extraordinary precision across millions of miles of space. And it worked. The impact measurably changed Dimorphos' orbit around its parent asteroid. It shortened the orbital period by an amount that was clearly, unambiguously detectable from Earth. For the first time in the history of our species, we nudged an asteroid on purpose, and we measured the nudge. That is not nothing. That is genuinely one of the more quietly remarkable things humans have ever done. So when I tell you the response, half of planetary defense, barely exists, I am not telling you we know nothing. We proved the core concept. We proved that a kinetic impactor can move an asteroid. But look closely at what DART actually was. It was one test, a single mission, against one small, conveniently located, completely non-threatening object, planned and built and flown over a span of years. It was a science experiment, run on a comfortable schedule, with no clock ticking. And here is what DART was not. It was not the beginning of a standing capability. There is no fleet of impactors sitting on launch pads. There is no warehouse of ready spacecraft. There is no protocol with a button. No chain of command that converts a detection into a deflection on a timeline of weeks. DART proved the concept, and then the concept just sat there. Nothing operational was ever built on top of the proof. And I want to be precise about what proving the concept does and does not give you, because it is easy to hear the words kinetic impactor works and assume the problem is basically solved, just waiting to be dusted off. It is not like that. DART told us that if you hit an asteroid with a spacecraft, the asteroid moves, and it moves by roughly the amount the physics predicted. That is enormously valuable. But it is one data point against one type of asteroid with one particular structure. Asteroids are not all the same. Some are solid chunks of rock. Some are loose rubble piles, gravel held together by almost nothing, and a rubble pile responds to a kinetic impact differently than a solid body does. Some are spinning fast. some slow, some you would want to hit, and some you would not dare to, for fear of simply shattering them into a shotgun blast of smaller pieces still headed your way. Knowing kinetic impact works in principle is the first chapter of the manual, not the whole manual. And the rest of the manual, the part where you have studied enough real objects, built enough hardware, and run enough missions that you could respond to a genuine threat with confidence, that part has not been written. We have the first chapter and an empty binder. And the reason that matters so much comes down to physics, specifically the physics of how you actually move an asteroid out of Earth's way. You do not blow it up. That is the movie version, and it mostly is not how this works. What you actually do is change its speed by a tiny amount, a small velocity change, and then you let time and distance do the rest. Because the asteroid and the Earth are both racing along their orbits, a tiny shove applied to the asteroid does not move it sideways in any dramatic way. What it does is change when the asteroid arrives at the crossing point. Nudge it a little, and over months and years, that little change compounds. And the asteroid arrives at the intersection early or late, and Earth is no longer there. The rock crosses our lane through empty space. But notice the words I just used. Over months and years. The entire method depends on having time. A small velocity change applied years before a potential impact moves the eventual impact point by thousands of miles. Plenty to turn a hit into a clean miss. That exact same velocity change, the identical nudge, applied just days before impact, barely moves the impact point at all. The asteroid is already at the crossing. There is no runway left for the small change to compound across. The physics of deflection is forgiving when you have time and brutal when you do not. Time is not a nice to have in this business. Time is the whole game. So now walk the realistic scenario with me. Suppose a genuinely city-threatening object is found tomorrow. Not 2026 JH2, which misses, but the next one. The one that does not miss. And suppose, because our detection of mid-sized objects is so incomplete, that we find it with a few weeks to a few months of warning. What happens? What happens is that there is no mission ready to go. There is no impactor on standby. The response would depend on improvising, from scratch, a spacecraft, a launch, a trajectory, a targeting solution, all of it, against a deadline measured in weeks. And every day spent improvising is a day stolen from the only resource that makes deflection physically possible, which is lead time. The clock is not just running. The clock is the enemy. And this is the moment to tie it straight back to the rock that is passing us on Monday. 2026 JH2 gave us 8 days of warning. 8 days is enough time to do exactly one thing. It is enough time to point a telescope at it and stream the flyby live so the public can watch a faint dot move across a star field. The Virtual Telescope Project is going to do precisely that. And that is wonderful, and I will probably watch it myself. But understand what that live stream represents. 8 days is enough time to observe. It is not enough time to act. If 2026 JH2 were coming straight at us, the live stream is still the only thing on the menu. We would gather around and watch it come. That is the terrifying truth the title of this video is pointing at. Not the rock, the hole where the response should be. And here's the part that takes this from a scary abstraction to something happening right now in plain sight. Because 2026 JH2 is not even arriving alone. 2026 JH2 is the headline this week. It is the close one, the photogenic one, the one with the live stream. But it is not the only rock with an appointment. If you pull up the public close approach tracking lists right now, the tables that the people who follow near-Earth objects keep and republish, the middle of May 2026 looks unusually busy. start with one object in particular. A few days before 2026 JH2 makes its pass, another small asteroid, designated 2026 JM2, went by Earth. And here is the detail that should make you sit up. 2026 JM2 passed at roughly 0.1 lunar distances. Let me put that next to our headline, Rock. 2026 JH2, the one getting all the attention, passes at about 0.237 lunar distances. 2026 JM2, which most people never heard a word about, came in at about 0.1. It passed closer. The one that got the coverage is not even the closest pass of the week, and it is not just those two. Across roughly a single week in the middle of May, the count of objects passing closer to us than the moon climbed into the high single digits. A whole string of small near-Earth asteroids, most of them sliding by within or just beyond 1 lunar distance, packed into about 7 days. 2026 JH2, at its size and its proximity, sits near the close end of that group, and by some accounts it may be one of the closest flybys of the entire year. But it is one entry on a crowded list, not a lone event. Now, I have to be careful and honest here, because this is exactly the kind of fact that gets twisted into something it is not. A crowded week of close approaches sounds alarming. It sounds like the sky is suddenly throwing more at us. So let me ask the real question directly. Is this a genuine physical clustering, a real pileup of rocks aimed our way, or is it something more boring? It is mostly the more boring thing, and the more boring thing is actually the heart of this whole video, so do not tune out. The most likely explanation for a crowded close approach list is not that more rocks suddenly appeared. It is that our telescopes have gotten dramatically better at finding small, faint objects than they used to be. The survey systems have improved. The detection software has improved. And so a week that looks like a wave is, in large part, the surveys finally catching up to a population of objects that was always there. We are not seeing more rocks arrive. We are seeing more of the rocks that were always arriving. Here's the way I want you to picture it. Imagine Earth is moving through a shooting gallery. Not a dramatic action movie shooting gallery, just a region of space that has a lot of small debris moving through it on a lot of different orbits. Most weeks, we see almost none of the rounds go by. They pass, near or far, and we never knew they were there, because they were too small and too faint, and we were not looking in exactly the right place at exactly the right moment. Then, occasionally, you get a week like this one, where the timing and the brightness and the survey coverage line up, and suddenly we see a whole handful of them at once. The crowded week is not the shooting gallery getting more dangerous. The crowded week is the rare week when the shooting gallery briefly becomes visible. And I want to be honest about the other half of that, because I do not want to oversell the boring explanation either. It is not purely an illusion. Small bodies are not scattered perfectly evenly through the space around us. They get nudged and grouped and shepherded by the gravity of the planets, by orbital resonances, by the slow drift of their paths over enormous spans of time. So, a modest, real clustering of objects on similar orbits is physically possible, and it is not a fringe idea to wonder about it. But here is the key distinction. Wondering whether there is a small real signal buried inside a week like this is a legitimate scientific question. Concluding that the sky has turned against us because a tracking list looks busy is not. The responsible reading is that this week is mostly improved eyesight, possibly with a faint real clustering inside it, and that disentangling the two is itself an open research problem, not a settled fact you can panic about. The instinct to notice the pattern is good. It just has to be pointed at the data carefully, instead of at the headline. And when you look at it that way, the crowded week of mid-May 2026 is, in one real sense, good news. Better detection is exactly what we have been saying we want. The telescopes catching 2026J M2 and 2026J H2 and the rest of the week's list. That is the detection half of planetary defense doing its job, and doing it better than it could have a few years ago. But, and you knew there was a but, the good news comes with a sting in it. Because here is what the crowded week is really showing you. Every single object on that list is one we could see. They were bright enough, well placed enough, caught in time enough to make the list. The crowded week is not a picture of the threat. It is a picture of the visible portion of the threat. It is the slice we are equipped to detect. And that is exactly why this week matters for the central problem. The crowded list takes the warning time gap, which can feel like an abstraction, like a statistic, and it makes it concrete. It puts faces on it. 2026 J M2, closer than the headline rock and barely mentioned. 2026 JH2, 8 days of warning, a live stream, and nothing else we could do. These are not hypotheticals. They went by, or they are about to, and they are the ones we caught. The objects you should actually lie awake about are not on this week's list at all, because they are the ones that never make any list, until the night they stop being an astronomy story and become a news story. The crowded week is the rounds we saw. The problem is the rounds we do not. There is a reason I keep saying the objects we should worry about are the ones that never make the list. It is not a figure of speech. There is a specific, physical, well-understood reason that a whole category of dangerous objects is essentially invisible to us. And once you understand it, the 8-day warning on 2026 JH2 stops looking like the bad case and starts looking like the lucky one. Think about how a survey telescope on the ground actually finds an asteroid. It needs the object to be lit up. It needs sunlight bouncing off the rock and traveling to the telescope. And it needs the patch of sky where the rock is sitting to be dark enough that the faint reflected light can be picked out. That means survey telescopes do their work at night, looking out into the dark part of the sky, away from the sun. Now ask the obvious follow-up question. What about the objects that are not in the dark part of the sky? What about the rocks that, from our point of view, are sitting in the same direction as the sun? Those objects are lost. An asteroid approaching Earth from the sunward direction, coming at us from the general region between Earth and the sun, is hidden in glare. It is up there during our daytime, washed out by the brightness of the sky, drowned in light. A ground-based survey telescope cannot pick it out, because you cannot see a faint moving dot when it is sitting next to the single brightest object in the sky. That entire approach corridor, the sunward one, is a blind spot. Not a hard spot, a blind spot. We do not see well there. We mostly do not see there at all. And this is not a theoretical worry. We have a case study, and it is the one I mentioned at the very start. Chelyabinsk, Russia, February 2013. The object that exploded over that city came in from the direction of the morning sun. It came out of the daytime sky, and it was detected by no one. Not late, not partially. No one saw it coming at all, because it arrived from precisely the blind spot we are talking about. It was somewhere between 17 and 20 meters across, near the lower end of 2026 JH2's size range, and it still detonated with the energy of roughly 400 to 500 kilotons of TNT, blew out windows across 6 cities, and sent about 1,500 people to seek medical attention, almost all of them cut by glass. The first warning anyone on the ground had was the flash in the sky, and if you want the upper edge of what this size class can do, you go back further to 1908 and to Tunguska in Siberia. The Tunguska object was bigger, somewhere in the range of 50 to 60 meters, larger than 2026 JH2. It exploded above a remote forest and flattened an estimated 830 square miles of trees. 830 square miles. the energy estimates run from several megatons to over 10. If that had happened over a city instead of empty Siberian forest, it would be remembered as one of the worst single-day disasters in human history. Tunguska is the reminder of what the top of this size range is capable of, and Tunguska too arrived with no warning at all, because in 1908, there was no system to give one. So now, hold the crowded week from a moment ago up against the blind spot. Everything on this week's close approach list, 2026 JH2, 2026 JM2, all of it was found because it was visible. Bright enough, far enough from the sun's glare, well placed for a survey telescope to catch. The crowded week is, in the most literal possible sense, the half of the picture we can see. And the existence of the other half, the sunward half, the half that holds objects on the exact same kinds of orbits, but coming at us out of the daylight, is the reason the warning time problem is not academic. It is the reason 8 days is not even the worst case. For an object that comes from the blind spot, the warning time is not 8 days. It is 0. It is the flash. And here is the thing about 2026 JH2 specifically. The thing that should reframe how you feel about Monday. We found it 8 days out. That feels short, and it is short. But we found it 8 days out because it came at us from a direction we could actually watch. It was in the dark sky. It was catchable. That is the lucky part of this story. That is the system getting a fair chance and taking it. The unlucky version of 2026 JH2, the version that should actually unsettle you, is not a version that gives us 7 days instead of 8. It is the version that comes from the glare and gives us nothing. So the question that has been building under all of this finally has to be asked out loud. Is anyone actually building something to close these gaps? The dark sky gap, the sunward blind spot, the missing response half? Or is this just the permanent condition, the way it is, and the way it stays? The answer, and I want to be fair here, is genuinely mixed. And the good part of the mix is the part that never makes the headline. I have spent a lot of this video describing a gap, and I do not want to leave you thinking nothing is happening, because that would not be true. Something is happening, and on one side of this problem, it is happening fast. The detection half of planetary defense, the half that finds things, is on a genuinely steep improvement curve right now. This is the good news, and it almost never makes it into the coverage of a flyby like Monday's, so let me give it the airtime it deserves. Start with the new generation of ground-based survey telescopes coming online. These instruments are not modest upgrades. They are a step change in how much sky you can scan, how deep you can scan it, and how fast. To give you a sense of the scale of the jump, one of these next-generation observatories, in a single early run, in essentially its opening operations, reported detecting something on the order of 11,000 new asteroids. 11,000, including dozens of new near-Earth objects picked up in one early batch. That is not a telescope nudging the numbers up. That is a telescope rewriting the discovery rate. The pace at which we are finding and cataloging objects is climbing steeply right now. And then there's the piece aimed directly at the blind spot we just spent an entire part of this video worrying about. There is a dedicated infrared space telescope that has been in development, designed and built for one specific purpose: to hunt the dark, sun-approaching objects that ground-based surveys cannot see. It is planned to launch in the latter half of this decade, and the reason it matters is the reason it uses infrared. Let me explain why that single design choice is so important. A ground telescope looking for reflected sunlight is helpless against an object hiding in the sun's glare. But an asteroid is not just a mirror. It is also a warm rock. It has been sitting in sunlight. It has absorbed heat, and it glows in infrared, in heat light, whether or not it happens to be well placed to reflect visible sunlight back at us. An infrared telescope, especially one positioned out in space rather than under our atmosphere, can catch that heat glow. It can, in effect, see the objects that are hiding in the daylight, because it is not looking for their reflection. It is looking for their warmth. A telescope like that is a tool built specifically to turn the sunward blind spot from a total blackout into something we can actually monitor. It is the answer, on paper, to Chelyabinsk's approach corridor. There is one more thing worth saying about why putting that telescope in space, rather than on a mountain, is part of what makes it work. Our atmosphere, the same air that keeps us alive, is a problem for infrared astronomy, because the atmosphere itself glows in infrared and absorbs a lot of it before it ever reaches the ground. Heat light from a distant warm rock has to fight through all of that. Lift the telescope above the atmosphere entirely, park it out in space where the sky is genuinely dark in infrared, and suddenly that faint heat glow has a clear path to the detector. Combine the right wavelength with the right location, and you have an instrument that can do the one thing every ground-based survey fundamentally cannot. It can look toward the sun's direction and still pick out the objects hiding there. So put the scorecard together honestly. On detection, we are improving, and not slowly. New ground surveys are multiplying the discovery rate. A purpose-built infrared eye is being ready to cover the blind spot. If those instruments perform the way they are intended to, the warning time picture for the mid-sized population of objects could genuinely shift within a few years. That is real. That is worth being encouraged by. I am not going to stand here and pretend the picture is all darkness, because it is not. But, and this is the but that the whole video has been walking toward, look at which half of the scorecard all that good news lives on. Every bit of it is detection. Finding things. Seeing things sooner. Seeing things in places we could not see before. And detection was already the strong half. The half that works. Now look at the other column. Response. The ability to take a detection and actually do something with it. And that column has one entry in it. DART. One test. One proof of concept flown years ago against a harmless target on a relaxed schedule. And nothing, still nothing, has been built on top of that proof. There is no operational deflection capability being readied to match the pace of the detection improvements. There is no fleet being assembled. There is no standing system. So here is the uncomfortable shape of the actual situation. The detection half is accelerating. The response half is standing still, which means the gap between the two halves is not closing. It is widening. We are getting better and better and better at seeing the thing coming, and we are no better than we were at doing anything about it once we see it. We are building a more and more powerful pair of eyes, attached to a body that still cannot lift its arms. And that brings us to the most honest way to think about Monday. Because finding 2026 JH2 faster, finding the next one even faster than that, only actually matters if finding it leads somewhere. A warning is only worth as much as what you can do with the time it buys you. So what does our system, the real one, the one we actually have, do with the time? And there is one object that answers that question better than any other by showing us the complete opposite of 2026 JH2. Let me introduce you to a different asteroid. Its name is Apophis, and in almost every way that matters, it is the mirror image of the rock passing us on Monday. Apophis is big, not house-sized. It is several hundred meters across, in the size class that genuinely concerns planetary defense people, the regional devastation class. And Apophis is going to make a very close, very famous pass by Earth in 2029. When it comes, it will pass closer to us than some of our own satellites, and it will be bright enough to see with the naked eye from parts of the Earth, an actual point of light moving across the sky. Now, that probably sounds like the setup for something frightening, a several hundred-meter asteroid making an extremely close pass. But here's the thing. The 2029 flyby of Apophis is calculated to be safe, a clean miss by current calculation. And the reason I am bringing it up is not to scare you. It is the exact opposite. I am bringing it up because Apophis is what a warning done right actually looks like. We have known about Apophis for years. We have known it was coming, known roughly where it would be, known the 2029 date, for a long time. And because we have had years, look at what that time has bought. It has bought the chance to observe it carefully, again and again, and refine its orbit until the uncertainty shrank away. It has bought the chance to study the object itself, to plan observation campaigns, even to plan spacecraft missions to go look at it up close. And, critically, if Apophis had turned out to be on a dangerous trajectory instead of a safe one, those same years would have bought the one thing that deflection physics absolutely requires: lead time, runway, the room for a small nudge to compound into a clean miss. That is the shape of a warning done right. Years, not days. Time to study, time to plan, time, if it ever came to it, to act. And now set Apophis next to 2026 JH2, because the contrast is the entire lesson. Apophis. Large, known for years, studied at leisure, a long, calm runway. 2026 JH2. Small, faint. Found 8 days out, streamed live, and gone by Tuesday. Two completely different experiences of the same basic event, an asteroid passing close to Earth. And the only variable that separates them, the thing that makes one a manageable science opportunity and the other a reminder of our limits, is warning time. Here's the part that ties the knot. Most of the tens of meters population the size class 2026 JH2 belongs to, the Chelyabinsk and Tunguska class, looks like 2026 JH2. It does not look like Apophis. The objects that get the Apophis treatment, the years of warning, are mostly the big ones we have already found. The smaller, more numerous, still city-threatening objects mostly arrive on the 2026 JH2 schedule. Short, sudden. Days, if we are lucky and they come from the dark sky. Nothing, if they come from the glare. So Apophis is the proof that warning time is the whole game. With years, you have options. With days, you have a live stream. And the entire job of the system we are building, the surveys, the infrared eye, all of it, the real measure of whether it is working, is whether it can turn more of the 2026 JH2s into Apophyses. Whether it can find the small ones early enough and far enough out, that days of warning become years of warning. Because years of warning is the only kind of warning that the response half of planetary defense, such as it is, could ever actually use. By the time many of you are watching this, 2026 JH2 is close. Maybe it is hours away. Maybe it has already happened, already slid past us at 56,500 miles, already given the astronomers their data, already faded back into the dark it came out of. The livestream will have run. The faint dot will have crossed the star field. And the headlines, the ones that ran newly discovered asteroid to safely pass Earth, will already be moving on to the next thing. So let me leave you with the most honest version of what just happened, or what is about to. The system worked. I want to say that clearly, because it is true, and it matters. A telescope in Arizona caught a faint, fast, house-sized rock. The data moved through the network the way it is supposed to. The orbit was calculated, the pass was predicted, the world was told. That is the machine running correctly. And the machine running correctly still meant 8 days. That is not a contradiction you are meant to resolve. That is the fact you are meant to carry out of here. For an object this size, the system working as designed and a warning of about a week are the same sentence. we have proven we can nudge an asteroid. DART was real. The concept is sound. But we have not built anything that could act on a few days of notice, or a few weeks, or, honestly, for most realistic scenarios, a few months. We have a magnificent and rapidly improving pair of eyes, and almost nothing behind them. The detection half races ahead. The response half has not moved. In the crowded week, the string of close approaches that 2026 JH2 was just the most visible member of, that was not the sky turning hostile. That was the solar system briefly letting us see what is normally invisible. It was the shooting gallery flickering into view for a few days. The rocks did not start coming. The rocks have always been coming. We just usually do not see them. This week we saw a handful, and even the handful we saw included 2026 JM2, closer than the headline rock and barely named, and 2026 JH2 itself. 8 days of warning and a front row seat to our own helplessness if the trajectory had been just slightly different. So the real question, the one I want to leave sitting in your head after the video ends, is not will an asteroid hit Earth. Something this size hits the planet on a long enough timescale. That is not a mystery. It is a certainty with a clock on it. The real question is whether the gap between what we can see and what we can do gets closed before the trajectory that comes back around is the one that does not miss. Whether the eyes we are building ever get a body to go with them. Whether we turn detection without response into something that actually deserves the name defense. Because the most truthful thing that can be said about a Monday evening asteroid is not, it is safe. It is something a good deal heavier than that. It is safe. And if it had not been safe, we would have found out at exactly the same moment, with exactly the same 8 days. And we still could not have done a single thing about it. 2026 J. H2 will pass. The live stream will end. The headlines will move on. And that 8-day number will still be sitting there. Quiet, unglamorous, unsolved, waiting for the next rock to come along and make it matter.